complete statistic. So the joint statistic is sufficient, but we have to check like whether it is complete or not. So for that, like we have to construct a non-zero function of two sums whose expectation is identically 0 for all theta. So if I consider u as summation xi and v as summation xi square, so if I consider a function h of u comma v minus nv square plus u square plus n minus 1 u, so we can see that expectation of xi is theta and expectation of xi square is theta plus theta square. So expectation of u is nothing but n theta and expectation of v is nothing but n into theta plus theta square, and expectation of u square is n theta plus n square theta square. So expectation of h of u comma v is nothing but minus n into theta plus theta square plus n theta into n theta plus n square theta square plus n minus 1 into n theta. So that means this is nothing but minus n square theta minus n square theta square plus n theta plus n square theta square plus n square theta minus n theta. So that means it is nothing but 0 for every theta. So that means there exists a function h which is not almost surely 0, for which like this function is 0 for all theta. So that means the statistic h u comma v is not complete. Now if we consider the fourth option, they are saying that summation xi square is a complete sufficient statistic. So if we consider summation xi square, this alone is not sufficient because the joint density depends on summation xi as well as summation xi square. So dropping this summation of xi loses information. So even if it were sufficient, completeness would fail for the same dimensionality because of the reason like shown here. So therefore like option D is false, option C is also false. The correct answer would be A and B.